Hey there. I don't know how many times I said it and I kept forgetting to do it. I'm going to do it now. I actually went through and ran it and I got more than 64 slots. But that thing still pointed at itself. But maybe I'm just going by remember what I recall and this table kind of. I don't have my definition here. I'm in a special project with everything turned off. So I got 83, right? And Lex PLI is 00, and the other one was supposed to be 2C, 7FFDF. This thing keeps changing. I remember it changing all the time. Yeah. 7FFD. No. This one. 7FFDF000. Okay, that's got to be the thing. Although this is different than what we got before. There it is. See, though, it's got to be right because this thing's always pointing at itself, and that other thing didn't change. And these are all filled with the numbers. That's decimal. This is the trick if you're ever in a bind and you want to, there's an array of things, but it's not your things, right? It's some other thing that points to an array of stuff, right? And you want to get the debugger to give you a list of all the elements instead, because it's declared as a pointer. It only shows you one element, right? So you invent a struct, and whatever the type is, the thing being pointed at, declare that as an array, as big as you want. I chose the exact size, and then declare a pointer to that, and set that equal to the address of the thing, the actual pointer value. If I want to see this as an array, like this value plus this offset, right? That's all you get. It just gives you an empty thing. So the only way to anything to do with arrays, where you want the array to behave like COBOL or something, where it really is an array, you just declare a struct. And I haven't copied anything. I just made this struct's address equal to the address, this address, FDFF10, right? DFE10. Oh wait, it's this one. 7FFDFE10. 7FFDFE10. And so it has a member that's an array. Great. So I wanted to be able to see them going in. Now this is, I'm not using common or anything, so nothing's been initialized or anything. So that means that the starting point happens to be at position 2. Now we're doing set value. Oh, 3, sorry. Oh, that's right. I switched this around for no good reason. I don't know why this is not coming out red. It's changing. Yeah, it's clearly changing. It was coming up red before. PTLS. I think it's just the debuggers. Too confused. Whoops. You see how it's doing that? Jumping around? God knows. But anyway, at the end of the day, you get down to here, and this shouldn't have gone up beyond 63, right? Which is the last value that could have been handed out in the array. It's in here somewhere. Printed out. But I don't know, maybe it has to do with the second one. 7F. I know how tedious this is. I'm trying to avoid doing it. I'll check this one and that's it. 7F F D 0 0 0. That's I know what that one is. That's the environment block, right? The PEB instead of the TEB, the thread environment block. I actually have that. No, I have the program environment block. I found this struct online. You never find these structs in the Windows headers, and that's actually part of this story and the magic trick I wanted to do, and the reason why this is called time warp and everything. So the answer is I don't know. You can get more than 64, but where they go is. It's gotta be some. I gotta have my. I'll do that test again with the with my struct there. Then I can have a map on top of that data of the whole region. Okay. Now, for what I wanted to do, and this is the thing that I read about in this guy's story, the article from 1995 or whatever this guy wrote, that is still the main reference for structured exception handling. If you recall, well, he has this example, and I'm going to show you the example. I'm not going to take credit for it, for being clever, but I don't think you had to be that clever to figure it out. Given the following, it is clever, but you don't have to be Albert Einstein or something. First off, I had to make special changes to the compile settings and stuff because I think probably this compiler may be the last one ever produced that will allow me to do this. to do what I'm going to do. I had to override something. I had to override a setting that prevents me from doing what I'm going to do. For security reasons. You're not allowed to do this thing for security reasons. But if I can't do it, well, then there's no magic trick, is there? What I'm going to do is the following: what he did, and I'm going to reproduce it, hopefully. If I've got the settings all set up right, I'm going to take it as given. Somebody's come up to me, and I don't know anything about structured exception handling or anything. In fact, this is the way he begins talking about it. He says, if whatever you think you know about it, just forget about that and just pretend you don't know anything. Somebody comes up to you and says, hey, I just found out that Windows NT, the operating system, if there's a fault or an exception, something bad happens in your code, it will call an application-defined callback function that you can write yourself on that event, and you can, depending on what you can do whatever you like. But you could, for instance, fix the bug or something and have it resume and stuff like that. Great new feature. They just added it to the new 386s. Okay, so how do I use it? Well, I don't know. But it works. Okay, well, that's pretty useless information. You told me about a thing and didn't tell me anything about how it works. Yeah, well, it turns out that nobody knows how it works. I mean, the people that write the compiler know how it works, but they're not talking. They're keeping it secret. And this is the situation, right? For some reason, the two main compiler vendors, Microsoft and Borland, kept secret, pretty much secret. They'd never published the code for the structured exception handling, for how they implemented it. I suppose you could have, maybe with the disassembly, you could have worked it out that way or something, but it was never published. However, if you taking it by questions, first off, a function gets called if an exception occurs. That's the assertion. All right. So question A. I have the questions written down here. A. So we're given an answer, and now we're going to ask a question. What does the function look like? What would it look like? Well, that part is given. It's in now. That's why I left that file there. Except.h, line 59. Now, starting from here, it only gets easier. Okay, line 59. This is the declaration for an exception handler function that gets called. All right. So we have this. Now I don't need to include this because it's already included with this. Okay. Now it's the function I want to have called. Let's say I won't call it that. I'll call it my function. Now this here is just some enumeration of integer value. Alright. Now, I don't know if you've seen these in-out things before, but these are just reminders that they're number defines, and they tell you about what the argument is, how the argument is to be used, but they aren't anything. It doesn't. None of these things is actually resolved to anything. See, they're all just blank. Everything, they're all blank. It doesn't matter. So you can, well, we could leave the hints in, but let's go with what he had to work with. He managed to figure this out without any more information than we've been given. He went looking for, the words exception, and he found in the header files that declaration, and did basically what I just did. Wrote this down. Now you could also write this if you want. This is C++. You could write that. I happen to have, so those are other ones with the underscores are typedefs, and these are these are typedefs, and the other ones are the definitions. Okay, for me it's easier to read with the colors. So I know what's changing and what's, especially when somebody's using their own naming convention. It's different from mine. This helps. All right. What's the what is an exception record? Well, it's in a header file. Well, it should be in a header file. Oh, it came up before. Maybe I gotta close this and delete something. Wait a minute. What did it just came up there? What was that? Well, I got it on count. Hang on a second. I gotta stop this. There was a thing, and a thing came up, and I'm used to that happening when I'm encoding a video, right? And it just, I naturally took it for granted that I was encoding a video, that I wasn't encoding a video. So I don't know. It's on camera, and we're going to see what it is in a minute. I'm going through this little story here, telling it, freshening it up, giving it a new life, an old story with new life, provided by me. Back to the time warp. Oh, maybe that was good. But it's still updating. Yeah, here. But the other one should have worked too. That's probably, but maybe if I just gave it a minute, it should work. It's there. Now it knows where it is. Now it doesn't. Well, Anyway, but that doesn't matter. The point is, we found it this way. Oh, no, it just found it a second ago. You saw it, right? Now it finds it. It's in a confused state. Alright, okay, now an exception record is this, so we can at least copy this and have a look at what it's got in there. Code, flags, a point, I think you recall this thing, right? A pointer to another exception record. The address where the exception occurred, some number of parameters, and I assume that that is the number of elements in this array, which has a maximum of this many parameters, exception parameters. So we get exception information and this, and that's what this first thing is. As far as these codes go, apparently, they can be found here in winnt.h. Somewhere. Something's going to say access violation. Search for access. Just like I do in my registry. I was trying to get rid of all that Microsoft Office. Okay, here we go. All these things that start with status are the error codes that come along with the message. It's the reason for the reason you got called back on is in this format. Access violation happens to be C00005. Never heard that number before. Okay. So what else? Now, establisher frame is a pointer, void star, and we are to take his word for it that we're not going to find out anything about this. As important as it is, we won't find anything about it until much later on. The header file doesn't tell you anything. Context record, now that, you've seen that one before. Whoops. Alright, remember this? Okay, so that gives us all these registers and extended registers and the stuff that you saw before. So this is starting to look like structured exception, right? We're getting an exception occurred and we're being returned in a function all these structures. 4 of them, in fact. Now what's going on? Okay. And this last one, dispatcher context, like the second one, there's little or nothing to be found in the header file. You have to dig deeper, but already we've got lots of information, and so okay, it's looking great, right? Only question is, okay, I've got my handler. How do I get the operating system to call it when an exception occurs? No, I want to reread what he said so I don't get it wrong. Okay. Yeah. How do you get it? How do you get it to call back? Well, that much. If you search around through them header files, probably the same one. You're gonna find a lot of use of the word registration. Okay. Exception registration record. And you'll notice that this exception registration record happens to be in a struct labeled something TIB, right? Now, I don't know if they were as explicit back then as this is now, but clearly this seems to have something to do with registering maybe your callback, right? And that is what he guessed. But he searched and searched, and you'll notice that I hit F3 again, and I didn't get another match on this thing. And it's mentioned apparently in many header files. It's the same struct, but there's no definition given anywhere, and there still isn't. There's no definition of this structure. It's just declared as as it is here. Since it's a pointer, you don't have to define the layout of the struct, right? That this is 4 bytes and this is its type, but we don't need to be able to see the members in order to construct this other struct. So, but he didn't give up, and he found you see now in those days Microsoft was also working on this thing called OS2. OS2, Operating System 2, I guess is what it stands for. It died eventually, right? But this was going to be, it was either going to be Windows or OS2 was going to take over the PC market. I don't even know. I don't think I've even seen it running, but it was a big deal back then. And apparently, so since Microsoft was working on OS2, and OS2 also had structured exception handling, a lot of the code between the two projects was the same. And he stumbled across, and it's like going through some assembler source, an assembler inc file, like .inc is what they use for instead of .h. And he found, this is me, I was going to bring this up. Where'd it go? Oh yes, exception registration. He found a similarly named thing in an inc file. And he says what the name of the file was. I got his whole story written down here somewhere. In this file? No, it's not here. It's in here, one of these documents. Yeah. But I didn't want to be seen too much at once. So he goes looking through, trying to find any information, and he finds this thing called bsaccept.h. For the IBM OS in the IBM OS2 header files. And like I said, the mechanisms were similar or the same almost. And then eventually, here, we found this. So now we've got this. This is in assembler. You declare a struct, what they call a struct, in this way. DD means D word, and I don't know about the question mark. Oh, this is an initialization value, so this means uninitialized. This is garbage. You can start out garbage. So this is a single double word called prev, and a single double word called handler. See? Now, so his guess, first guess, alright, it looks like, this sounds like that other registration thing that we saw before, right? The only difference, there's like one word different. Exception registration record, exception registration, puts 2 and 2 together and figures, okay, this is the structure. This is the structure that contains a pointer to a function called a handler, right? Remember, this one had the word. I didn't change this part. That already said handler. So, and so that's always what go on. All he's had to go on is what somebody said, right? What he knew about the 386. 386 has that feature, and that the Windows NT, both Windows NT and OS2 purport or do support structured exception handling through the try and the except, right? But then no source code. But he wants to see how it works. So now what have we got? We've got a structure. We know the format of what the handler would look like, right? And we've been told that the operating system is set up, for no compilers or anything. The operating system is set up to call an arbitrary function of our choosing, but now we know what kind of function it is, and we know what kind of structure it would appear in, and we also can see that there's a linked list of these things. So what's the obvious question? What's the obvious next question? I mean, we got all this stuff. We know the format of everything. Question is, well, you should hit pause if you haven't already thought of a good question to ask. The good question that he asked was, okay, well, where does it go? Where do you put this structure so that the operating system is going to call it when a bad thing happens? Well, you could look at the disassembly of things, but you can also use the thinking thing and realize that since structured exception handling is a per thread thing, an exception happens in the context of a thread, that wherever this structure goes, it's got to go somewhere where you can put thread local data, right? And so he just guessed. It's not much of a guess, but well, what about maybe somewhere like fs:0, but maybe not one of these structures, or maybe he tried it, but he tried that maybe, and then the second natural try would be a pointer too, and that turned out to be the answer. The answer is at fs:0, we have one of these things, star. Okay, so that means that star fs:0 is equal to well, will give us one of these structs. Is a thing, right? Okay. So first things first. Oh yes. Now this is also a linked list, right? And it turns out that the way these things work generally is you push things on the stack, and so well, let's just write the function first. I've got code. I've got a version of his code here. Here's the handler. Now, what he does is he invents a bug, a crash. Okay, and here I've just written out the same thing. Now, I don't know why he's declaring an int here. He doesn't do anything with it. But he does declare an int there, and there might be some reason why. I don't think it's an accident, because he does the same thing again. he does a declaration for no apparent reason in main. Now I'm just going to show you the code. Make it easier. So what we want to do is we want to generate a crash, and we want to get this thing to get called, knowing that there's a pointer, that we need to put a pointer to one of these things at this address, right? Okay, so that's what we want to do first. Now, for some reason, he says the word, what do you call it? I guess handler. It's on the next page. Let me see if I can remember. I'm going to cast that function as a D word. This is how you would cast that as a D word, right? Now I'm going to assembler. What we need to do is create one of those structs on the stack. Okay. So the stack goes down. So the first thing we need to do is push handler. Step 1. Now we need to push a prev pointer, right? The previous exception record has to be the first thing in the struct, so we have to push that. I don't know if we can do it in one step, I forget. I think we can. Okay. Now on the stack we have one of these structures. Prev. The stack grows down, so it's handler, and this here is pre. Because if there were an exception registration registered already, right? Then it would be at that address. So now we're adding a new one to the list, and we're pushing the previous one on the stack. And so therefore on the stack is one of these structs. And now all we've got to do is replace the previous value of prev with our thing. So we've got to move into fs0. We're going to move there. We need a struct like that, right? Oh, we've got one. Right. Okay. Ours is ours is this thing. Oh, okay. I see. Sorry, I got it backwards. All we got to do is push ESP here on the stack. Sorry, move ESP into the 0 position, because on the stack is this structure, right? So that points at one of these structures with our handler. Simple as that. So the reason why he's done this on the stack apparently is because that's the way that the compilers actually do it, and they put the thing on the stack, and then if the next person does the same thing, then that's, I guess, saves the this is a way of allocating memory for the struct, right? Such that it can be retrieved, I guess. It's on the stack anyway, it's safe, it's there, it can be brought back somehow. It's like a sort of like a stack, a weirdo way of setting up a stack frame. In any case, according to theory, now if we create a crash, now he repairs the crash by fixing EAX. So we put EAX 0, and then we try to put something in there. 1, I think he had. We put 0, doesn't matter what value. So this is crash. Okay. Now, in theory, if this is going to work, then we're already ready to go, and this should bring us into the handler, and if we return this particular value, the processor will resume back here and try and rerun the operation. Okay? Oh, now we gotta, what he did here is he's put something, a valid value, I'm gonna invent this valid value into EAX. Something we might recognize. Okay, so we put the address of that into EAX, and the next time through, it should not crash. Then we print something else. Okay. Now, just like a function call, we've pushed something on the stack, so we need to repair our stack. When it returns, these 8 bytes that we've pushed on the stack will not have been taken off of the stack. Even if it isn't our thing, no, I guess it would be ours. If our handler gets invoked, then it stops here and resumes here. So what's left on the stack are these 2 extra things that we push, so we gotta add 8 to ESP to clean up the stack. It's a strange way of calling a function, but that's essentially what it is. Now, calling this function in the meantime makes no difference because this has no net effect on ESP. We could do this before or after, it doesn't matter. Okay, now we'll compile. Now, see, there's going to be a warning that comes up, and I did a special thing to override what the compiler would do to the program that would disable, that would make this fail. Okay. You see, nowadays, any function that you want to put into this special magic area has to pass like the compiler forces it to pass a test, basically. It's got to take an exam, and our function hasn't taken any exams, just sitting there. However, at version 8 of the compiler, you're able to turn it off, and in the exceptions, I turned off the access violation exception. Oh, I'm gonna turn it off again. I turned it back on. So that's off. That makes no difference to the compile. And I hope I've done this right. I'll put a breakpoint on in the handler function. We can find out if this gets entered by putting a software breakpoint there. The breakpoint, this is a hardware interrupt. This is placed by software. Okay, handler, some value. Push it. Push the previous value on the stack, and so yeah, it doesn't matter whether that gets lost or not. The reason we're putting that there is to create the proper structure. So now all we need to do is point fs0 at the structure, which is ESP should be pointing at it. And now when I try to do this, there's your magic. You see, that, what I've just done there, okay, is invoked an exception handler from the operating system. The language, C++ or whatever, anything, was not used. All we did was set up the situation that you have to set up to invoke a user-defined function on a crash and have it pass all these various bits of information. Now we're going to repair the bug by putting something valid in EAX and return this value, and I'll put a breakpoint here and here because I'm not sure where it's going to go. Okay, back on this line, resuming this line, no crash. This should be 0 now. Oh. I did put the address of scratch on that. It's too late. What is it? It's not too late. So 461. That could be the debugger can't work it out, right? We've kind of cheated. Anyway, it went there. You saw it happen. Oh, that's why. Maybe you can't figure it out because of the stack, even though it's not used for this. No. I think we're okay stack-wise, but it'll get the usual crash if it isn't. It wasn't. I'm curious about why the move didn't work, but that's not the point that I was trying to make. You have just seen a demonstration of the operating system in action, invoking a custom handler for an exception with no special language trickery or keywords or anything. It works by putting one of those structures into the 0 position in the thread information block, and then if you cause an access violation, the operating system knows to read here and add 4 and call the function with those parameters. So there's your magic for the day, and I hope you can try it yourself and impress your friends and see if you can figure out, as I had to, how to get your compiler to allow you to do this, because it took me a while to find the special switches. You'll notice that if the thing would come off, there's no exception handling on here. There's no all these exception handlings turned off for one thing, and there's also another switch to deal with that, the warning to disable, to allow me to do what they call unsafe structured exception handling, and probably by version 9 if they won't allow it. Okay, see ya. I went to see. I felt like I'd forgotten to do something with this cleanup, and I had. We forgot to bring that previous one back into FS0. But remember, ESP is still pointing at that struct, and the first element of the struct is the prev. So we put that in AX, put AX in FS0, and then restore the stack. If you restore this first, then well, actually, we're probably safe to restore it first, because this is thread local, right? A thread switch can't touch our local stuff. Okay. Oh no, but the stack could get the data on the stack could get wiped out. Could it? No, it can't. It doesn't matter. You could do it before or after, in keeping with tradition. Use the memory and then free it. Don't free it first. So that one addendum, this restores the previous handling. So I guess that's the other reason why you put it up here on the stack, is to put it in a safe place so you can restore it.